What is the purpose of a genetic algorithm? We started talking about it last time, but I want to go over, I want to make sure you have the really high level view of them. What does a genetic algorithm do? Yeah, that's kind of what it does. I guess I want to ask, why are we doing it though? Well, let's do it in terms of a utility theory tree or a uniform cost search tree. Imagine you have this big tree that represents all the choices you can make. What is a genetic algorithm doing in terms of those choices? Yeah. That's a good way to put it. Yeah. So you know how with uniform cost search, we exhaustively search the tree. And with utility theory, we are basically computing the whole darn thing so we can be sure our math is exactly correct. But one of the biggest problems with those algorithms is cost. They just don't, it's not efficient to try every possibility in the universe to make a decision. Usually humans have to make decisions without having thought about everything, right? Couldn't you live your life much better if you could just freeze time and go think about things for a while, and then unpause time, and then go make the choice, and then freeze time again, and you'd never make a mistake, right? You'd be ready to face every decision you ever made, but you can freeze time. So in the real world, we have to make decisions while we have a finite amount of time to explore our decision tree. And that's what a genetic algorithm does, is it tries stuff. One semester, I had the students do a path search with a genetic algorithm. So this is your starting point, this is your goal, and we used a genetic algorithm to find a path there. Well, instead of doing this uniform cost thing where it builds these frontiers that go all the way to the goal, the genetic algorithm ends up doing kind of these lightning strike things, where it finds these paths, and the paths kind of wiggle their way to the goal. And why are they all wiggly? Because they're sort of random. It's just mutating these paths, and they just mutate more and more. But what happens over time is it starts off eventually finding a terrible path to the goal, and that path improves itself and improves itself. And by the time they're done, the paths end up looking kind of like that. Not optimal, but pretty darn near optimal. And why does it look that way? Because that's what a genetic algorithm does. It searches the space, but non-exhaustively. And its main heuristic, the main thing that drives a genetic algorithm, is that when it finds something that you deem as good or fit, then it's more likely for that path to propagate. So this path is going to spawn children, and those children will mutate. And can you kind of see that by making lots of copies of the best thing we've found, that path is going to be refined and refined, while some of these other paths that are really dumb are going to die and not be propagated and not be they're not going to survive. And so it focuses on the stuff that's good, and usually that means it finds the right way down the tree, ish. And by ish, I mean it'll never find the truly optimal path, but it will almost always find a pretty darn good one. Okay? Are humans optimal? We could argue it a little bit, but you know, here I am. I have eyeballs that have blind spots in them. Did you know you have blind spots in your eyes? There's that optical illusion thing where you put a dot over in the right spot and you look at this dot and then all of a sudden that dot disappears. So there's that. There's the fact that here I am talking through the same orifice in which I also eat. And sometimes that makes my throat dry, and you know, there's a little switching mechanism down in there. Why? Because genetic algorithms don't do the exhaustive search, right? They didn't try every possibility. There are a lot of ways we could have turned out that we didn't, but hey, it found something that worked because look, here we are at a university, I'm teaching stuff, we have knowledge. It looks like humans are pretty darn effective. So, it has been argued that genetic algorithms are the most effective optimization ever, as evidenced by, ta-da, here we are. So, at least we know it can produce some pretty darn amazing things if done effectively. Okay, so a genetic algorithm is an optimization technique. You can optimize whatever you want with it. In our case, we're going to be optimizing the weights of an artificial neural network. What is an artificial neural network? Yeah, a giant pile of linear algebra. A neural network is a model that's been inspired by the human brain. Here's what we know about the human brain. It's probably the least understood organ in the human body. It's the one we haven't yet built a replacement for. That's what this class is all about. We're going to try. We can build an artificial heart, right? And that works because it's basically a pump. Your brain has a whole bunch of cells in them that are called neurons. A neuron is just a cell, but they look a little different than other cells in your body. And the prominent difference is they have this thing called an axon. An axon is a great big rod or a big stringy thing that's poking out of the cell. The main body of the cell is called the soma. There's a nucleus in it. There's a lot of mitochondria in your neurons because they generate electricity. And the electricity is necessary because what your neuron does is it fires a voltage potential down the axon. So think of it as a little electricity generator, and the axon is the telephone wire, the wire through which it shoots its signals. Now, the neurons, here's a more detailed model. Neurons are all connected in this great big network, meaning the axons of all these neurons are connected to the dendrites of other neurons through these synaptic connections. And basically, when one neuron fires, it stimulates the dendrites of another neuron. And when that neuron gets its dendrites stimulated, it gets kind of excited, and then it starts to fire. So what happens is the neurons are kind of just going around stimulating each other and making each other fire. Does that make sense? Imagine it's kind of like Facebook. If you posted on Facebook and nobody read your responses, that would be lame and it would die, right? But if you say something and then somebody says, ooh, that gives me an idea, and so that person posts something, and that stimulates an idea, and the ideas kind of evolve, but they're kind of triggered by each other, right? Isn't it the interaction we get from each other that causes you to go back and see if anybody responded to your post, and then if they do, people respond to their posts, and you get these signals just going back and forth and all around, and it seems to create some kind of intelligence or stupidity, depending on the social network. But nevertheless, there's activity going on, and that's what happens in your brain. These neurons stimulate each other, and they get stimulated and stimulate each other. And encoded within all of that electrical activity is your consciousness, all of your thoughts, the thinking that goes on in your brain, and everything the brain does is just this big network of electrical signals. So, we built a rather simple software model that's kind of like a brain. We'll just pretend I connected them all. You know what a fully connected network is like, right? Okay. Well, here are a bunch of connections, and now I'll build a big network out of it. A neural network is a model kind of like this. Each of these circles are simulated neurons, and the idea of a simulated neuron is it's just a number, and that number represents the electric potential between the neurons. And these weights, these lines, the axons that connect one neuron to the other neuron, we call these weights in a neural network. Think of it like this. If there's a number right here, I'll put a 3 and a 1 here and a -4 there and a 7 here. You take this number and you multiply it by all these weights. So suppose this weight has a 0.1 and this weight has a 0.3, a whole bunch of numbers inside of here. We take these numbers, we multiply them by the weights, we sum them up, and that's the number that feeds into the next neuron. And this neuron feeds its value, multiply it by a whole bunch of weights and sum them up and feeds it into the next neuron, and so forth. So basically there's a whole layer of neurons that feed numbers into this layer of neurons, that feed numbers into this layer of neurons, that feed numbers into this layer of neurons. And what finally comes out? Bunch of numbers. There's some numbers. Now, well, 2.1.23 is not a number, but that's because it's a typo. There, now it's like a number. So a long story short is a neural network is a magical box. Numbers go in and numbers come out. Let's really simplify this. We'll call whatever goes in X, And whatever comes out, I'll call y. X and y are vectors now, not just scalars. But if I feed in a vector of numbers and I get a vector of numbers, I could call this box f if I wanted to. Do you see that a neural network is a function approximator? Some numbers go in, some numbers come out. And what's actually inside the box, as far as we care, is just a bunch of weights. And the exact details of those weights, we'll say, are not even that important. All that matters is if you change the weights, it changes the function that the neural network represents. So at a high level, do you get what a neural network is? It's a function approximating device, and it's powered by weights. What's inside of the box is a whole bunch of linear algebra. If it helps you think about it, imagine a polynomial. You know how a polynomial has coefficients? And as you change those coefficients, it changes the curve of the polynomial, right? Well, here's what we're going to do in this particular problem. We're going to take, for x, we're going to measure a whole bunch of quantities, like the number of opponents on the screen, the distance to each of your opponents, the amount of energy that you have. Basically, I'll just call this conditions. Do you see how we could encode the conditions of this game into a vector? Well, we can. And what's going to come out of this agent is decisions. These decisions are going to drive the agents, and so your agents are going to go run around doing whatever the neural network told them to do, and the neural network will tell them what to do based on the weights inside of the neural network. Okay? So the only major remaining question is, where the heck are we going to get the weights? If we had a good set of weights, then our agents would behave intelligently and would do smart things. But where are we going to get the weights? Surely you know the answer, right? Yeah, we're going to use a genetic algorithm to evolve weights to drive the neural network to empower your agents to win the game. That's what we're going to do in this assignment. Is you're going to code up a genetic algorithm which can be used to evolve a bunch of weights, and if it works, then your agent will beat the opposing agent.